different, meaning really the mass. Okay, really the mass is different. So can you qualitatively tell me an assumption you can make about the differences between the temperature changes that's going to occur here?
The temperature is going to be lower than the last with the higher mass. So the temperature change is going to be lower.
It's going to be less of a temperature change than the one with low mass.
Okay, so you're saying which one will be double? Or sorry, you're saying less, but can you now assign a number to that?
Oh, like that one would be.
Okay, so because the Q is the same, there should be half the temperature change in the one with the higher volume. I mean, higher mass. Okay, so basically what you're solving for is what in this case? Both of these you're solving for delta T. Okay, so Q equals MCAT, and you're doing delta T is equal to Q over MC. Okay, delta T is equal to Q over MC. So Q is 2,000 joules for both of them. M is either 50 or 100. And the C is still the same at 4.18 joules per gram degree C. Your mass here is really the one determining the temperature change. So if you divide by 100, it's going to decrease the delta T, so that because it's spread over a higher volume, the temperature change overall net is lesser. So it's actually half. So in relationship to finding, like putting this in terms of a multiple choice question, it could say, what's the relative temperature change? What's the ratio of temperature change? It could ask that in many different ways. So don't think about I have to calculate 2,000 divided by 4.18. Like that's a little rough, right? Or even 2,000 divided by 50 times that or 100 times that. Think about the relationship between the two setups. You got me? Okay. So then does anybody have this value for the 100 one and the 50 one? So what's 2,000 joules divided by 100 grams? Sorry, so I'm doing this over here. 4.18 joules per gram degree C.
4.7.
So the temperature change 4.7 degrees Celsius, 78 degrees Celsius, okay? And so if you now have a 50 here, that's actually half of the mass, so it's going to be double the temperature change. So that's going to increase by what for the other one? Say again? So what is that, 9.56 degrees C. Okay, so you can look at that from a standpoint of multiple choice and think about how this could be formatted. All right, so in terms of the C value, because the C value is a intensive property, meaning that C value does not depend on the amount of mass, you have to consider the mass with it, meaning we had to include the mass because it is a point of contention about how much the temperature changes. So the C value has to be utilized along with the mass versus like in a coffee cup calorimeter, we have the heat capacity for it, not the specific heat capacity. So what's the difference between specific heat capacity and heat capacity again? So little c is joules per gram degree C, whereas big C is joules per degree C, meaning that you naturally that coffee cup calorimeter is going to have a specific heat capacity with it, meaning it has already the mass kind of contained within its constant. So every single time you have a coffee cup, you have to calibrate it to find the C value. Every specific time you have to find it and calibrate it. That's why we try to use the same coffee cups as we go. Yeah. This is mass, just mass. Not molar mass, it's just the mass of the. Well, it's not really molar mass or mass. It's a quantity that's related to the mass of your compound.
So like for H2O.
You don't. It depends on how much H2O you have. Like that's why I had 100 or 100 or 50. It's not based on identity really. It's just on the problem at hand.
What about the little c, like specific heat of water?
It's not. It's related to the mass of your substance, not the individual molar mass of the substance. It's like how much you have of it. Okay, we'll kind of go through some more problems with that. All right, so on this one, tell me your process of thinking of like how do you account for this difference in heat? So if you had, this difference in temperature. So you have 40 grams at 54 degrees and 60 grams at 20 degrees C. What's the temperature of that? It's going to be the final temperature upon mixing. Who's an idea of how to get started here? Any idea will work. So you're saying at the grams, okay, and then do what? Okay, well, see, that's combining the two. I liked where you're going, but then now I don't. Let me step back. Emma, did you have something? So start with your given, start with make a table. So like you have enough information to do Q of the cold water, I'm sorry, the Q of the hot water and Q of the cold water. You could separately do two different Qs. Okay, but you don't really have the delta T the T final for either of these, but you have the T initials for both of these, right? Okay. So it says initially this sample of water starting at 54, initially this sample of water starting at 20. But you both end at the same temperature final because we're mixing the waters. Okay, you could set Q equal to Q or MCAT equal to MCAT, where that T final is a variable defined. Okay, that's the harder way, I think, but it makes a lot of sense. What's the nice trick maybe we could use? Alvin, do you have anything?
I was going to say do that and then solve for T final.
Okay, I'll show you that sample here. I want to show you how that's solved here, because that's exactly how it's solved here. But I want to think outside the box in the next phase of this.
T1 minus T2, set up like that.
But who's T2?
Older one. Could you do like 54 degrees Celsius minus 20 degrees Celsius?
No, because then you're not, remember delta T is always T final minus T initial, and so both of those are initial, so that would be inappropriately finding delta T. So I know we can do the Q equal Q or MCAT equals MCAT. So, and again, you'll see that this is degree C here, they put Kelvin here, and I'm going to tell you why. It's naturally, it's just a degree difference or a temperature difference. So despite the fact they have Kelvin here, your temperature change is still going to be in degrees Celsius because that's what we're referring to. So ignore that for now. But T final is what we don't know, right? So we put our mass in our mass, our C value, our T final minus our T initial, or T final minus T initial. And as you're going through this, you'll see that pulling the T finals to one side, you can eventually get there, but you're going to have to divide by your mass and divide by your C values first. So you divide by those, you happen to get T final minus 54 degrees C divided or multiplied by that division work there, which ends up being 0.667 because 40 over 60 is 2/3, right? 1 second before I go there. So 40 over 60 is 2/3, so that's how they get this 0.667, and they're setting equal to the T final minus 20 degrees, and then distributing, and then subtract or adding, and you get 33.6. Does everybody know what's happening between this step and this step mathematically? I can math it up here, but I'm trying to show you your shortcut as well. So we could go through all this work, which I think is pretty tedious, and find 33.6 should be the average, should be that difference. Or we can think about it in terms of, I got water and water. I got water hot and I got water cold. Tell me what you're going to say.
Okay, I was going to say you take the ratio of the first grams to H2O, so it's 4 over 10.
Right, okay, so we have 40 grams, 60 grams.
Yeah,
so that's
the total of 100 grams. So you get 40 over 100, 44.
okay.
Yeah, 60 over 100. You take the temperature of 0.4, which is 54 degrees, and you multiply that by 0.4. And then you take the temperature of 60 degrees.
And that's exactly what I was going to do first. Thank you. All right, so this is a shortcut. It's supposed to be, if you can think about it in terms of proportions. So 0.4 is 40% of the overall sample is a 54 degree sample. And then 60% of the overall sample is a 20 degree sample. So the math's not, I'm not saying the math is easy, but it's quicker, right? Because those same variables are applying to both sides. So if we totally wipe out the C value, it helps us. And if we totally wipe out the masses in terms of masses and make them ratios instead, I think it helps us. So 0.4 times 54, whatever that is, say again, 21.6 degrees Celsius plus you can do this in your head, 0.6 times 20, 12. So 21.6 plus 12 is 33.6. I think this is a much easier process than this one, but this is a lot more chemistry sane than this one is. But think about in terms of how you're going to expedite your process on mental math. Okay, can I move from this question? Thank you. Okay, so that's calorimetry in a box for you. Let's do one more shot at calorimetry, make sure we're good here. And let's think about how we're before we approach it, please. Let's think first. So in example one that we just did, the temperature only reached 31 degrees Celsius, not 33.6. The final lower temperature would be due to the heat from the warmer water being transferred to the calorimeter versus the cooler water. So what would be the heat capacity of the calorimeter? So in the end, it's asking for heat capacity, right? What the heck is that? One more time. Well, that's big C is equal to joules per degree Celsius. Okay, so we have to find these individual pieces, and then we're going to divide them. So joules. How are we going to find joules?
Q equals the mass of the 40 gram.
Okay.
Times 4.18.
Joules per gram degree C. Okay.
54. Or no, I guess it'd be 31 minus 54.
Yeah. So this is Q of hot, right? Q of hot is 31 degrees C minus 54 degrees C. Right, so that's the heat released.
Yeah. And then you do the same thing for 60, then you change temperature. And then you subtract both of them, and you divide that by the
Whose temperature change?
cold water.
The cold water's temperature change. And this is exactly what you guys did in your lab. This was your hot water, cold water example where you're calibrating your coffee cup calorimeter. So this is a Q difference between hot and cold. And so when you subtract, you find the heat loss that wasn't contributing to the cold water. And then you take your Q difference and you divide it by your temperature change of the cold water, because the cold water is the thing that's not getting the energy it should, so it's going to the coffee cup. So that difference in temperature change is going to be the coffee cup is able to contribute back to the total heat in itself. So difference between heat loss and heat gain. So this is our heat loss, which is our hot water, minus our heat gain, which is our cold water, and we find the heat gained by the coffee cup calorimeter. That's our heat difference. So it's just magnitude differences here. When you have your negative there in the front, it just means that it's exothermic. And then I'll tell you that total here is 1,090 joules. So this is, I'm assuming, to be positive right now because it's being absorbed, right, endothermic absorbed by the coffee cup. Good? You see how mathematically Q was MCAT minus Q, or MCAT minus MCAT? Okay, sometimes semesters walk through the process and you can write down everything you want to, but I am videoing too. And then separately, the cold water went from 20 degrees Celsius to 31 degrees Celsius, so that temperature difference is 11 degrees Celsius. And so when you take your Q divided by your temperature change, it is in reference to the thing that's doing the absorbing, which is the cold water. So you divide by 11, you get 98.7 joules per degree Celsius. So you're doing Q divided by delta or temperature change. Yeah.
Why in your equation right there did you subtract the heat gain instead of 90?
Because it's the magnitude difference between them. So this is a negative, right? So whatever, I think in this one, I think I just rearranged the equation. Truly, I think this is this, and this is this. And this is like this is an example from College Board that I was looking through to kind of give you guys a better explanation of setup from College Board. So I just pulled their data from there. So I'm assuming all this math is right. Okay. In terms of coffee cup calorimeters, we can find we can calculate our big C. Yes? Okay. So that's everything from last week. Now we're going to talk about enthalpy. Enthalpy is an evaluation of heat transfer, but we are specifically talking about heat transfer under constant pressure because we're talking about our atmospheric pressure being like our room, not bomb calorimeters all the time. Those are not under constant pressure because that's like a steel drum, and if you explode something in there and it's making a lot of gases, what's going to happen to the pressure? Like really high pressure, right? But it's constant volume because it's a steel drum. The steel drum doesn't change volume. So we can talk about both of them, but I'm like 90% of the time talking about constant pressure, very few times talking about bomb calorimetry because it'll actually say the word bomb calorimetry in the problem. So I have a couple of things that we're going to walk through because since we're not here tomorrow, I'm going to practice some in class with you, leave you to practice some more on your own tomorrow, okay? So when we talk about enthalpy, we're talking about usually chemical reactions, like heat of reaction is kind of how it's termed. Heat of reaction like this, RXN, or sometimes you'll see heat of solution, which is what you've done in your lab for the past 3 days. You'll see heat of neutralization, NEUT, neutralization. it can be really anything. Heat of fill in the blank. Because it's talking about the reaction, it's talking about a solution process. Now, delta H can be found in like 5 different ways. So at the end goal is to always find delta H. Delta H has to be found from data from a lab, from values in a table, from calorimetry. I mean, it can be really from anything. So I'm trying to do one sample of each on how do you get to delta H in the end, and how do you apply it in a example problem. So we're talking about delta H. The one that we really have a lot of exposure to is the one where we dealt with our lab. And I'm just recapping the lab one more time because this lab should be 100% done by Wednesday. Pre-lab explanations, error analysis, everything, the whole works, except for the part that talks about comparisons to your class data. All right, so what we did in the lab is we took our compound, we broke it apart by overcoming its intermolecular forces, and that is actually called the lattice energy, but we took it and we overcame its molecular forces so that it would disperse. And then we had the waters themselves, water versus water. We actually overcame its intermolecular force called the hydrogen bond. And so those were 2 endothermic processes. This required energy, and then at the end, you guys saw the temperature either rise really high or drop pretty low. And so at the end, it's the amount of energy that it took to kind of make it a full-on solution. And so for this one, your sodium chloride one, which some of you guys did in your hand warmer lab, was actually in the end colder. And that's because overall it was an endothermic process, and the way we display that is we say delta H of solution is a positive 4 kilojoules per mole. Endothermic being positive. Got me? So this stuff you are a little bit familiar with because you've done your part of the lab, but now we're talking about the delta H aspect. So I will tell you that delta H enthalpy is always going to be Q per mole. And if you forget this, then you're in trouble. You will use this oh so often. So how many ways do you know right now to find Q? Q equals MCAT, so we can say Q equals MCAT to find Q. That's probably it right now. Okay, for Q equals negative Q, you can find the system and surroundings. You can find Q of phase change by doing delta H times moles, which is exactly what this is. Delta H times moles gives you Q. So you know how to find Q. We're going to find a couple of other ways today. And then moles is just going to be based on the compound in question. You take your grams to moles, you're good. Once you divide, we call that enthalpy. So we're going to learn how to kind of do that through various ways today. This is actually just one way to find it. Okay, so constant pressure. I don't think I need this really. I'm going to skip the theory for now. Okay, so we talked about the enthalpy of reactions. Those are sometimes called molar heats because it's referred by mole, by per mole. So molar heat of reaction would be kilojoules per mole or joules per mole, just based on like the question at hand if it's talking about kilojoules or joules. Heat of neutralization. It's called heat of neutralization because it's a neutralization reaction. What the heck is a neutralization reaction again? Acid. So acid plus base yields water and a salt. And I'm going to put BA. Okay. So acid plus base yields water and salt. So that would be heat of neutralization. Heat of combustion would be so maybe a hydrocarbon, for example, plus oxygen yields CO2 and H2O. So what you can imagine is that this one is likely going to be in a bomb calorimeter because it's exploding something. It's a combustion problem. Whereas heat of neutralization or maybe heat of solution like this might be in a coffee cup calorimeter where you have a solution and you have to figure out am I adding the reactants masses or not. I'll give you a tip on that too because sometimes that's really College Board's gone back and forth on it, so I finally figure out what I'm going to do today with you guys so it's not confusing. Okay, and then the last thing is standard heat of formation. So standard heat of formation is a very, very particular definition. That's why I had you guys read your MSMI thing with your definitions, because it's related to the formation of 1 mole of a compound. So the formation of 1 mole means that when I write my balanced chemical equation out, I can't form 2 moles of it or 3 moles of it. I have to form 1 mole of it. So for example, let's form water. Form 1 mole of water from its elements. What are its elements? So how do I write hydrogen always? Diatomically, okay? How do I write oxygen always? Oxygen O2. So, but if I can only form 1 mole of this, I actually get this the only time ever you can use fractional coefficients. So what's my fractional coefficients I need here? So 1 hydrogen, 1 1 times 2, 2 hydrogens, I got that, and then 1/2 of an oxygen. So this is what I mean by heat of formation reactions. It's formation of 1 mole of the product from its elements. So its elements can be diatomic if they're naturally diatomic at standard temperature, which I'll show you what standard temperature is in just a second. But it also has another couple of conditions that apply. So the other conditions that apply to assume standard is 25 degrees Celsius, 1 atmosphere, and 1 molar solution. And that's what this little knot right here means. If that little knot is up there, it's telling you these conditions exist. So you can use this special table, and I'll show you where the table is in your book. It's in like Appendix 4 of your book. But it tells you every single heat of formation, or delta HF. Delta HF tells you every single enthalpy of formation for every compound that we'll deal with. And so you'll utilize those if needed, and I'll tell you why you'll use them shortly. So the point then, this will take me about 2 years to realize, kid you not, I did not realize the difference between standard temperature and pressure for gases. What's standard temperature in gases? So 273 Kelvin or 0 degrees Celsius. Standard temperature and pressure is gases. Standard conditions is thermochemistry. Standard conditions, okay, is the one word that's different, but it does not mean the temperatures are the same as the standard temperature and pressure. It's 25 degrees Celsius, not 0 degrees Celsius. So just note that there's a big difference between those two, gases and thermochemistry, and that the reason that this exists here is because a lot of times we do these things at room temperature, so we consider them standard temperatures, because room temperature is a nice kind of warm. 0 degrees Celsius would be really, really cold if that were the case, if you're doing that labs in that condition. Okay, so that's what the knot means, and now let's keep going from here. So in terms of writing chemical equations, yes, okay, I printed out a couple of things for you, not everything, so bear with me. I'm going to kind of flip back and forth between these. So if we're writing a chemical equation now, we're going to call them thermochemical equations if they have a delta H associated with them. So the delta H is still kilojoules per mole, or joules per mole, except when it says per mole, it's relating to the moles of the products or the moles of the reaction or reactants. And so this mole of reaction that's back here, I don't think I have that on your paper, so this is an old copy. So do put /mole reaction. College Board just like 2 years ago changed everything from delta H as being kilojoules to kilojoules per mole reaction. So we're going to be relating this to the coefficients as needed. So I'm going to show you that through an example though. Learn by doing, right? Okay. So if we have a reaction that's endothermic, our delta H value will be positive or negative? Positive. If I have a reaction that's exothermic, delta H will be negative. So make sure you're associating the endothermicity or exothermicity by sign change. Okay, so in terms of this reaction here, let's read it first, then we'll write our chemical equation. Thermochemical equation will come at the end. And when I say thermochemical equation, it's just the inclusion of this at the end. That's it. It's the only thing that's different, as well as some states that we'll have to write down. So when 5.8 grams of methane, what's methane? CH4, burns, meaning it's combusting. When it burns, it releases 320 kilojoules of heat. Okay, so that's released, so I'm going to put that as a negative. So I'm just kind of writing down my givens first. Write a thermochemical equation for this reaction. First off, let's just start by writing the chemical equation. What's the chemical equation for this reaction? Methane, and methane is probably a gas, plus oxygen, which is likely a gas, creates carbon dioxide, and that's a gas, and water. And water, usually it'll be water vapor at hydrocarbons below 3, so like propane, ethane, and methane. So this is probably a liquid. Let's go with that for now. Okay, so balance it by, what, a 2 here, and a 2 here. We're good? Is that right? Yes, okay. So we've got this balance now, and I'm considering this in reference to methane. So I have 1 mole of methane. I haven't like done any coefficients on methane. All right, so all I need to do now is find delta H. So to find delta H, you need Q divided by moles, right? So delta H is heat over moles. Well, I already have the heat, right? That's released from what? This, but that's in grams, right? So what do I need to do? convert that to moles. So sometimes the way, and you'll see this in on my answer keys when I post them, you'll see me do like this. 320 kilojoules, 20.0, sorry, kilojoules is released per 5.80 grams of methane, and then just do a little stoichiometry right next to that. So this is how much heat's released per gram, per 5.8 grams, and then you'll multiply by or use the smaller mass to convert to moles. So 1 mole of methane is 16 grams of methane. So that allows me to cancel my grams, and then you have kilojoules per mole. Yes? Okay, Alvin, you got me? I have this too, just over here. So 883 rounded. Okay. So I'm doing 3 sig figs because of this right here. Okay. So that's negative 883 kilojoules per mole. And that, my friend, is delta H. So all you do is for this thermochemical equation, you're going to write the delta H at the end. It's not added to the products. Please don't put a add to the product at the end. Just write delta H equals negative 883 kilojoules per mole. That's it. Can I get a thumbs up if that makes sense? I don't want to leave you in the dust, but I do have a number of questions I want to do today. Okay, so in terms of thermochemical equations, it's just the addition of the delta H at the end, and delta H is Q divided by mole. However you get Q, you got to get Q. So in terms of this one, now that we know the final, we know this relationship here, we can use that as a conversion factor, because this is related to every single compound in this question. So this is how much heat is related to the combustion of 1 mole of methane, 2 moles of oxygen, 1 mole of carbon dioxide being produced, or 2 moles of water being produced. So this can be related to each of these based on their coefficients being like a mole ratio. Okay, so in this case, it's saying it's still referencing methane, nothing else, so it makes it kind of easy because that's that per 1 mole of methane. So calculate the amount of heat produced when 25.1 grams of methane react. What do you want to start with? Okay, so 25.1 grams of methane converting to moles by dividing by 16 grams. Please put your identities down as well. I'm modeling to you how you should show your work. Okay, so then we got to grams, got from grams to moles, and then what do I multiply by to get to heat? So I'm saying that, and since it's sitting phrasing it in heat produced, it's okay if you don't put the negative because it's saying that much is being produced, is being released. So I'll put the 883 right here. Kilojoules per what? Per what? 1 mole of CH4. Because that would be different if it was like 25 grams of water was produced, right? We convert water to moles of water, and then if it were talking about water, what would we put down here? For every 2 moles of water, it would be related to the compound at hand. Yeah. So when you see how the question's phrased, it says being produced. So what you could say is, X amount of joules is produced versus being that negative sign on the front. So it just depends on how you phrase it. Yeah.
Is delta H like in kilojoules per mole?
It's generally in kilojoules per mole. So in this one, I do have it in kilojoules. So this would be in kilojoules here. And so that would be kilojoules here. Wherever you get. All right, give me a thumbs up if I can move on. I'm trying to kill you, but I am trying to give you everything you need before we go. Because our classes are a little shorter this week too. You guys know that you're going to homeroom. You know that? So today is a teal day. You go to homeroom, no like random teals. You go to homeroom for your normal teal. So juniors and seniors go to homeroom first, and then go to lunch second, and then freshmen, sophomores go to lunch first, and then homeroom second. And that's it for the whole week. It's all homerooms all week. Quiet study, so do your chemistry homework, please. Okay, so in terms of the chemical equations, just to recap, you do need your states of matter, because every state of matter has a certain amount of energy associated with it. So you absolutely have to put your states of matter with me. And then I told you that the degree symbol meant standard conditions, which, don't look at the board, what's standard temperature? 25 degrees Celsius. And then that these other conditions are related to the rest of it. And then lastly, when you write your thermochemical equation, you must include the sign at the end to indicate if it's endo or exo. So with this neutralization process, is this endo or exo? Exothermic because of the negative sign. All right, so that's thermochemical equations in a nutshell. Moving on. Let's do a quick example together on writing the equations again from the words, not really from I give you the reaction, but from the phrasing here. So standard enthalpy of formation of silver nitrate. So what does standard enthalpy of formation mean again? Okay, from its elements. Okay, so formation of silver nitrate means forming one what? Spell it out. Okay, 1 mole of HENO3, and that is forming, since silver nitrate is an ionic compound, right? Most ionic compounds exist at room temperature as a solid. That's using your logic of ionic compounds. Okay, so what are the elements that make that up? Silver, is that what's the state at room temperature? It's a metal, right? Plus? Not nitrate, that's not an element.
Oh, okay,
Nitrogen, how do I write nitrogen? Into, what's that standard state? Gas and oxygen, gas. And then what do I need? What do I need to balance? So what do I need coefficients wise? No. Formation of, right, remember this is formation, so this has to be a 1. So you balance with fractions. So half of a nitrogen, 3/2 of oxygen. So 3/2 times 2 is, the 2's cancel, you get 3, and you have a 3 here. Okay, so that's why they're a little different than normal. Standard enthalpy of nitrate, silver nitrate, is this. So for the thermochemical equation, I would have, I'm just not leaving myself enough space here, guys. Okay. I would have at the end delta H formation with a naught. It has to be written like that. Formation with a naught is equal to negative 124.4 kilojoules per mole. So that completes the thermochemical reaction. It's really easy, but it's really easy to forget too with the delta H formation at the end. Okay, standard enthalpy of combustion of ethanol. Quickly, ethanol. Combustion, right? So I'm starting with that, not finalizing. C2H5OH, and ethanol is likely what at room temperature? Thank you, liquid. Keep going. O2 gas, CO2 gas, and water as a
Yes. Oh no, it's higher, so it's like.
right. So this is from C1, 2, and 3 propane. That's going to generally leave you with water vapor. And balance with what? 2 here, and 6, so only 3 there, and then 4 plus 7. So what do I need? 7/2 here. Is that right? Double check my math. I'm sure it's good. It's okay. So delta H of what at the end? What do I label this delta H? Comb. Combustion, right? Comb. And that's negative 2,769 kilojoules per mole. So each of these are going to be related to different types of reactions. Yeah. Where? Oh, so the standard enthalpy of formation has to be per 1 of whatever's being produced. And generally, if you're talking about enthalpy of combustion for something in particular, that something gets the 1. So ethanol got the 1, and everything else bounced based on that. Good point. Yeah. It doesn't. Oh, so it does actually. It says standard. So standard, you still put the naught thing. I'm sometimes bad about that, so thank you for calling me out on that. If it says standard, you do have to put the naught. Yeah. These are just writing thermochemical equations based on your knowledge that you have to have the 1 that belongs, and you have your standard states, and you have to put the delta H at the end. We're not solving for anything yet. Okay. Now let's do 2 more like that. Enthalpy of vaporization. Standard enthalpy of vaporization of water. What do I start with? Now this says vaporization. What does that mean to you? liquid to, that's it, guys. Liquid to gas. Liquid water to, guess what? Gaseous water. Okay. And what do I write at the end? Delta H, not VAP, right? Delta H VAP, because it's from a vaporization, is equal to 43.99 kilojoules per mole. Okay, if I had said delta H of condensation, what would be the only thing different here? It would be flipped gas to liquid, and it would be negative, because this is an endothermic process, right? It takes a lot of energy to get liquid to gas. It takes positive 43 or 44 joules or kilojoules per mole, whereas if you were releasing it, it would be negative. So you can see how this could be flipped. Thumbs up? Questions? Okay, one more. Oh, this is the one, yeah, let's do this one. Enthalpy of solution of sodium hydroxide. So what do I write first? Hold up. So write the equation, but I'll write your delta H at the end. Delta H of solution, that's what you're saying? And then you said a not, and you said it's what? Negative 44.57 kilojoules per mole, right? So that's just that information there. But what's the process? In AOH, state of matter, solid is an ionic compound. All ionic compounds are solid at room temperature. And you're undergo a solution process. So you need to make it aqueous, perfect, and it's just aqueous. It's not really a chemical reaction, but you can put water up here to indicate that it's in aqueous solution, it's in water. And this process, we make aqueous, right? But is sodium hydroxide soluble? Group 1 metals. All group 1 metals are always, always, always soluble, meaning when I say soluble, I mean they do what? They ionize. Dissolve is a crappy term. We don't actually know what dissolve means. So this actually could be written how? Na1 plus aqueous and OH minus aqueous. That would be the best way to write it, as an NIE. Okay? Can I move on? Okay. Let me pause for a second, because I think this is where I want you to practice. Yeah. I got some time. I want you guys to take 5 to 6 minutes and work through question 1 and let's start with question 1, we'll see where we're at. This is on your enthalpy problem set, which is in your packet of all the problem sets, but I have on the board so you can see it just as well. I just want to make sure you're good, because you will be using this problem set for homework. Go ahead and do one now. Enthalpy. You're going to be doing the whole problem set. Let's start with number 120. Just an example of an equation on how you write that as an NIE by dissolving water. So you should model what we just did. This is the
So the reason, sorry, just realized why I'm typing this out. I'm prompting myself to tell you that the answers on the bottom of that enthalpy problem set, you see them? The first one and the second one I had to adjust based on me doing it wrong for about 3 years, to be honest. But that's because College Board changed their mind on how they wanted them solved. So let me find my enthalpy problem set real fast, and I can tell you what the correct answer is. Obviously, that's when College Board changes his mind, it's kind of a hassle. So
The correct answer is 1B is 20 or 2.1 kilojoules. 1D is negative 83.2 kilojoules. And 2, it's only 1 and 2, by the way, everything else is legit. It's only the ones in solution they changed their mind on. Number 2 is 227 kilojoules for one of those answers, and D, I think it was D on this one, and D is 20.2 kilojoules per mole. So, FYI, now you can actually check your work appropriately. For part A, did you guys put your NIE, calcium chloride solid with water on top of the arrow yields aqueous, 2 ions, CH2 plus 2 chloride, you put 2 chlorides as a coefficient, and then leave some room, delta H solution at the end, we'll figure out what the delta H solution is in a second. So how did you guys, approach Q, meaning B right here? So Q goes MCAT. I'm going to scroll up some, you guys have to look at yours because I'm running out of space. So Q equals MCAT is right here. So Q of what equals MCAT? So Q of solution is what's absorbing the energy from the reaction of calcium chloride with water. I say reaction really loosely there, but truly you should be thinking about solution and, a system and surroundings. So the surroundings is what's measuring that temperature change, but the reaction is truly what's causing that temperature change, that heat release. So it's negative, right? Because temperature up. Didn't the temperature go up? Yeah. Okay. So truly, you should be always remembering Q and the difference between system and surroundings. But regardless, you're still doing MCAT. So what's the M? How did you do it in your lab? Did you sum your masses of your salt and water, or did you have just water? You have to sum them, because at this point, the water is really intricate in making the solid break down, but the solid's really intricate in making that energy exchange, so they have to be together as one. So this is the part that College Board has decided it's going to be. When you have a solution formation, you have to sum your masses. So put MT for M total, but the C, this system is so dilute, right? We always assume those really dilute solutions have the C, the heat capacity of water, and that the temperature change is just whatever the temperature change is. So M here is 100 milliliters, which the density of water is 1, so 100 grams of water plus, what was it, 2.80. grams, and then 4.18 joules per gram degree C. And temperature change is what here? 4.9, thank you. And you did temperature final minus temperature initial. So when you calculate that together, you should get what? Anybody? So 2,100, I got 5.
I did 4.184.
Thank you, okay, so 2,107 point what? 16. Okay, so Alvin's is going to be just a little bit off for mine, but as long as you're close, you're in the right ballgame. So this energy is energy that's released to the solution. Yes? Okay, so that's going to be negative. So this process is negative. So even though the solution is absorbing it, this process as a whole is exothermic. That's why, oh, hold on, no. Is it exothermic? So, did I put a negative up there? Sorry, guys. That's a negative right there. On my process. On my answer key, it's a negative. Alright, so the process overall is a negative this many joules. But that's per how much calcium chloride? 2.8 grams, right? Okay, so we have the Q. Now, understanding that the process of the solution occurring and dissolving is going to be exothermic, so 3 or C is exothermic. How much heat would be absorbed by the water for only 1 mole of calcium chloride? Where does this is where we start where we kind of did today. Your negative 2107.16. I know we've not done sig figs yet, but ignore that for just a moment. This is how much energy is released per what? How many grams of calcium chloride? 2.8. And so, if I want to get that per mole, what do I do next over here? Yep, you utilize the molar mass of calcium chloride, so that's 1 mole of calcium chloride. Its molar mass is 110.9 grams. So grams of calcium chloride cancel, so we get joules per mole at the end, which is how delta H should be written, is joules per mole or kilojoules per mole. So that, mine's going to be a little off, so Alvin, take your value and divide that for me, or multiply that for me. Divide and multiply that for me. Because mine's a little different from yours now.
Negative 8,300, or just kidding. Negative 83,358.
Okay, huge number, right? And that's joules per mole. Anybody have time to write that numbers out like that? So generally when the number's like a couple thousand, when you go convert that to kilojoules, so that should be negative 83.5, right? Negative 83.5 kilojoules per mole. And that's how we should write it when we write our delta H of solution, negative 83.5 kilojoules per mole. To complete that thermochemical equation that we have at the top. Alright, let me know if I move too fast so that I have a thumbs up. You guys are usually quick on the pickup. Just making sure you're okay. Alright, so your second one, number 2, will be very similar to that. Now, the only point I did that one for is because they need to know the sum of the masses, or we should plug in for M. Okay? Good? Make sure you note that. Alright, so let's do one more. Do I want to do 3? Let's see if we actually want to do this one right now. Yeah, let's do this one real quick. This is not number 2, this is number 3. No, this is number 4. Number 4. Alright, so leave some space for 2 and 3. Let's sample this one. When 5 milliliters of ethanol is burned in a bomb calorimeter, the temperature changes from blah to blah. The calorimeter has a heat capacity of 13.24 kilojoules per degree Celsius. Determine the delta H of combustion, or the enthalpy of combustion, for 1 mole of ethanol. Write the thermochemical equation for ethanol. Now, we've already written the thermochemical equation of ethanol out, so I'm going to write that very quickly. So that's C2H5OH liquid plus O2 CO2. We just did this one like really, so I'm going very quickly here. And then 2, 3, and 7/2. Okay, so that's our equation, but then again, at the end, we're going to have delta H of combustion. We'll have to figure out what that is in a second. Now, is this one going to be exothermic or endothermic right off the bat? Definitely exothermic, because it's a combustion reaction. Combustion reactions always release heat. And you can see it's releasing heat to the bomb calorimeter, because what's happening to the bomb calorimeter? Okay, it's increasing in temperature, right? So it's getting hotter. So heat's being transferred to it from the reaction. So when 5 milliliters, which who cares about milliliters? We never use milliliters, we always use grams. So take your density and convert it to grams. So 0.789 grams per milliliter. Figure out that in a second. Is burned, the temperature changes, so delta T is T final, so 28.67 degrees Celsius minus T initial, 19.75 degrees Celsius. We'll figure out what delta T is. And it's telling us big C is 13.24 kilojoules per degree Celsius. Alright, so that's all of our givens, and you know we're converting that to mass. You guys tell me what you want to start with, and I'll tell you values. You know that we have to find delta H of combustion at the end. Delta H of combustion is always written as kilojoules per mole, meaning Q per mole, okay? But we don't really know a whole lot about the combustion itself. We only know the temperature change of the calorimeter, right? So, think about system and surroundings. Q, the calorimeter, is absorbing energy, right? It's being taken or being transferred from the Q, the combustion. So that's negative. So this is kind of our general idea of system and surroundings, calorimeter in the combustion reaction. What do you guys know that we could do over here? Say again? I can't do MCAT because the calorimeter itself, we don't know the mass of the calorimeter. But I can just do CAT. Okay, big C delta T. So Q, the calorimeter, is equal to big C delta T. Okay, so big C delta T, and I'm just going to kind of keep putting my work everywhere. Okay, Q cal is equal to 13.24 kilojoules per degree C. And then my degree C change is, what's this? What is it? 8.92 degrees Celsius. So when I take this and multiply, I get Q cal is 118.1 kilojoules. So this is my Q cal. This is my amount of energy that's being absorbed by the reaction. So it's just negative, right? So this is related to a negative Q combustion. So Q combustion is negative 118.1 kilojoules. All right, so that's probably the most important point to know right here so far. Because now that we're back and talking about combustion, we've switched from surroundings back to system. Now we're almost to delta H cone. But delta H cone is kilojoules per mole. So what have I not used yet for my givens? Grams of ethanol, which nobody cares about grams, right? What do we want to get to? Moles. So I've taken us from milliliters to grams of ethanol. Ethanol weighs 46. Nope, hold on. 12 plus 12 is 24. 16. Is it 46? Come on. 46. I could just look here. Yeah, it's 46. Okay. So 1 mole of ethanol weighs 46 grams. I'm so sorry I'm all over the place, but once I start, I just fill in the gaps, okay? So sorry. So milliliters to grams to moles is 0.08576 moles of ethanol. Okay, what do I do with this? To find delta H. Q over moles. So I got my Q of negative 118.1 kilojoules. Got my moles. I just need to divide, and I have my delta H. So taking that number down here to my other work, divide by 0.08, what was it again? 576 moles of ethanol. And I get my delta H of combustion, drum roll, negative 1377 kilojoules per mole. So 1,377 kilojoules per mole. That's a lot of energy! Holy cow! But remember, it's kilojoules, so that's even bigger in joules. Alright, did you guys follow? Combustion reactions, the masses are tricky. You have to think about, do the masses go with the calorimeter or with the combustion reaction? Generally, they're never with the calorimeter because it's a bomb calorimeter, and bomb calorimeters have the calorimeter being Q is equal to cat, big C delta T, so there is no mass there. So don't try to plug your mass into the calorimeter. The mass is from the combustion reaction. You have to find that towards the end. Give me a thumbs up. Questions anywhere? Yeah.
Yeah, what were you doing wrong?
So they used to tell us to consider this, so the water as the surroundings and the salt as the system. So we wouldn't add the masses. And then they were like, nope, solution process requires water and the salt to interplay together, so it's a whole AC together.
Do we have less accurate knowledge because we use a specific water?
It's so dilute, we don't account for that pure math easy. So yes, it is less accurate. I can only blow your head and make your brain so much bigger, and then college will do the rest. Okay? And they actually just, I was at UNC Show on Saturday, and they did a question like that, and they're like, yeah, students never know when to add it either. And I was like, oh, great, we're glad we're on the same boat. Okay. So now let's talk about delta H in other senses. So we have done this one. This is on your sheet, by the way, right? It's on your sheet? Yes, yes? Give me a heads up. I have about 25 minutes left. I'm going to keep going through a couple examples with you. This is related to your videos from this weekend. You should have gotten a good idea of like what Hess's law is versus the Big Mama equation, which is delta H products minus delta H reactants and so forth. So I love Hess's law. It's like a puzzle. It's great. It's really fun, actually. So we know how to do take Q divided by moles, and we can find delta H. That's from most of the equations we've been doing so far. One thing I didn't write down, but you may have seen it on the slide. So it says like delta H formation of elements. FYI, those are 0. Write that down someplace. Delta H formation for elements are 0 kilojoules per mole. I just thought it out when I saw something here. I just want to make sure I can tell you that before you leave. So I'll utilize that in a second. Okay, so another way to find delta H is by using Hess's law. And so we can do it indirectly through values from a table. Oh, right here. Free elements are always 0. Sorry, right there. You can do it indirectly from a table if you have a big, humongous chart of delta H formation values. And so a big, humongous chart could look something like this. So a chart like this, and you can just see it's called delta H formation, delta H standard, or delta H naught is how sometimes it's referred to, in kilojoules per mole. Or it could look like this. Tables galore, right? You have an appendix in the back of your textbook with all of these values. So they are labeled with delta H of formation, delta G of formation, delta S of formation. So make sure you're looking at the right column. So these are values that are associated with the formation of this 1 mole of this compound from its elements. So from an example standpoint, how do we find or how do we utilize those values? We have to plug them into this. This is an indirect equation to find the heat of reaction from the inherent enthalpy of reactants and the inherent enthalpy of the products. So the way you do this, and this is on your reference sheet for the end of the year, right, for your exam, you do delta H of reaction is equal to the sum, right, sigma sum, yeah, math, okay, sum of the product formations minus the sum of the reactant formations. So these values you pull from a table. So my table here is related to this question here. So the way we set this up, and write this down for yourself so you have an example for later, is you have to write down your kind of setup first, and then we'll plug in values. So delta H of reaction is equal to, who are my reactants? Products. Who are my products? So name this for me. Nitrogen dioxide. So I have 4 nitrogen dioxides. So nitrogen dioxide is right here. That's a positive 33 kilojoules per mole is associated with that per mole. So since I have a 4 here, I have 4 moles of it, so hence why I'm multiplying by 4. Cool? So 4 times 30, I'm actually going to plug in as I go, sorry, kilojoules per mole. Okay, so it's 4 times nitrogen dioxide plus 6 times, now water liquid is different than water gas. That's why the states of matter are so important here. So water liquid is negative 286 kilojoules per mole, whereas water gas is negative 242. So that's why it's important to write the state of matter. So 6 times negative 286 kilojoules per mole. So all of that right there, all of this right here in brackets in red, is enthalpy of the summation of enthalpy of formation of the products. So the sum of the enthalpy of formation of the products. Okay? Subtract the sum of the enthalpy formations of the reactants. It's a lot of words, but you know enthalpy of formation is delta HF. All right, so who are my reactants? Okay, so 4 times ammonia. Ammonia's delta H, thank you, negative 46 kilojoules per mole. You really have to cross your T's and dot your I's, like making sure it's positive or negative. Okay, so that's ammonia, and that's the sum, so you're adding it to 7 oxygens. Why 0? All free elements are 0, so it's not on the table. So you're like, well, she just didn't give it to me. No, you need to have it. You just have to know that it's a free element, so it has 0 kilojoules per mole. And do not neglect, don't be like, oh, I just don't do it, I just don't have to add it. You get a point for plugging this in. If you don't plug the 0 in, you don't get your point. They absolutely want to see that you know it's 0, not just like negligent and you forgot to add it. You see the difference there? They want to see you know it. So, all I do is plug in my calculator now. Plug in your calculator. Let's plug it in correctly the first time, please. Because I want you to put your parentheses and negatives and positives. Everybody plug in your calculator. Even if you just look like you're playing your calculator. I'm good with that. Act like you're doing it for me. So H of products minus H of reactants. Anybody? Confer with somebody else? Negative 1400? Okay, so it's sometimes like that doesn't have negatives and positives in there, you gotta just double check with somebody. Negative 1400 what? Kilojoules per mole of reaction. And so this again is delta H, right? So you can find delta H through standard values from a table from Q over moles if you have like a calorimetry experiment. So this is called, I always call this, it's called Hess's law, but it's just delta H products minus delta H reactants. And that equals delta H of reaction. All right, so that's another way to find delta H. Let's keep going. We have another couple ways to find delta H here. So I told you your values are in the back of your book if you need it, or just Google a big heat of formation values, and you'll find images on Google galore. And let's do another one. This is the puzzle one I like. Okay. So sometimes reactions occur very, very, very slow. Kinetics is our next unit. We'll talk about rates of reactions. So they occur by like 5 or 6 steps. Step 1, reactant 1 goes to product 1. Product 1 goes to product 2. Product 3 goes to product 4. Product 4 goes to product 5. And product 5 is our final. So there was like 4 or 5 steps that occurred. And that's like where we normally talk about, oh, all I care about is the final, is the initial and the final. But sometimes those individual steps have individual delta H's associated with them. So this is the Hess's law. I call it indirect too, but it's Hess's law of summation of balanced chemical equations. So we have to take each of our chemical equations and we're going to stack them on top of each other and cancel out things that are on the reactants and the products that are exactly the same, just like you would if you had a spectator ion on the reactants and products. And everything that stays should be in the final equation. But you can manipulate reactions. You can flip them, meaning reverse them. If you reverse a reaction, that means you've switched the sign of delta H. So if a reaction in the forward direction was originally endothermic and you flipped it, what have you done to it? You made it exothermic. So when you manipulate, which I have here someplace, okay, so if you reverse a reaction, you have to change the sign of the delta H. If you flip a reaction and you multiply every coefficient by 2, you again will do exactly the same thing to delta H. So you multiply delta H by 2. So I'm going to show you this through an example. But as you go, you always have to consider the final reaction because the final reaction should be your overall reaction. So this is from like a 2011 exam. So I'm going to start off with an easy one, which is to control reactants and products. And here are the two equations for you. So the combustion of carbon monoxide is represented by the equation above. Determine the standard enthalpy of change, so standard enthalpy of reaction, meaning delta H, for the combustion of carbon monoxide gas using the following pieces of information. So they give you baby step, carbon plus half an oxygen yields carbon monoxide. It releases X amount of energy. And then they separately give you solid carbon plus oxygen yields carbon monoxide, and that releases that much energy. But you want this. So I want that. So I'm going to write that at the bottom of my screen here. CO gas plus half an oxygen. Oops. Half a gas. Half an oxygen gas yields CO2 gas. And that's what I want my two reactions here to equal. Well, what you can see is that carbon dioxide is on the product side, and carbon dioxide on this one's on the product side. So this is oriented in the right direction. So I'm going to start off by writing this reaction out. C solid, plus oxygen gas yields carbon dioxide gas. And the energy associated with that is negative 393.5 kilojoules per mole. So what you'll notice is that this carbon dioxide and this carbon dioxide are the same thing. This is going to follow down with me. But this carbon right here doesn't exist in my final equation. So I have to find a way to cancel this carbon out by writing my next equation with singular carbon on the product side so it will cancel. You with me? Okay, so this reaction here, how do I write it down here? CO gas forms solid carbon and 1/2 of an oxygen gas. And so how do I change this? So if you reverse the reaction, you flip the sign. So what's the sign? Positive 110.5 kilojoules per mole. Okay, so carbon dioxide stays. Who cancels? The two carbons here, one carbon on the side, one carbon on the side cancel. Who else? So this half an oxygen cancels half of one of these oxygens, leaving me with half an oxygen. Got it? So basically, I'm just going to do like a half scratch, full scratch. Okay, so half of that one stays with us. So we have half the oxygen accounted for, the carbon dioxide accounted for, and the carbon monoxide accounted for. So everything follows down to the end, that doesn't cancel. And then what do you do with these? Just add them. So a negative 393 plus 110.5 gives me delta H of reaction to be negative 283. Is that right? Thank you. Kilojoules per mole. So, who likes this Hess's law? I hope that you like this one. I really like this one. Okay, this was an easy one. Let me go here. You guys do this one? Here's your target equation. Target equation. Yes, it's all you. Target equation. And this is on your sheet of paper as well, I think. You guys, you won't see me tomorrow. I'm stuffing your brains full of information so you can sleep on it. I have to look to see which is going to give me what I want. So so this is my target equation. So you're going to put that at the very bottom of your screen, or very bottom of your paper. And so if boron is on the reactant side, I'm going to keep this one as is because boron's already on the reactant side, sorry. But B2H6 is on the product side. But currently it's on the reactant side, right? So I have to flip this one. So I need this product side. Let's see how, let's through it first and then we'll go through it. I do have one more way to find delta H, but I'm hoping for this way. Yes. You got one too? We'll do it in the middle. Got a lot of chance of them. I love Hess's law. It's great. You'll soon fall in love with it. Just like a puzzle. So you can manipulate your equations by multiplying by coefficients, but if you multiply your coefficients, you have to multiply your delta H by the same thing. So I think probably we got here. We saw 2 bariums, we got 2 bariums. We know this is sticking with us. We know the oxygens cannot exist here anymore because they got to be gone. And we see this B2O3 can't stay with us. So what do you guys want to do next? Go ahead. Be specific. Yeah, switch the second equation you're reversing. Okay. Second equation you're reversing. So B2O3 solid plus 3H2O liquid yields B2H6 gas plus 3 oxygens. And so if I reverse my reaction, I take my sign and do what? All right, so I make it positive. So this is a positive 203 kilojoules. All right, so far, let's see what we've actually done. We know the B2, or 2B is going to stay with us. We know the B2O3 and the B2O3 there is going to cancel, right? We know it's going to cancel. That's good. We don't want that at the end. And we know the B2H6 is going to stay with us at the end. All right, so what else do we have to consider? We got like 1.5 oxygens here. We got 3 oxygens here. So I need what else on this side? More oxygens on this side, so all the oxygens will cancel. And I need some waters. I need some hydrogens. And I need to. I think the water will come. Where's my water at? It's right here. Okay. So I need 3 waters to cancel because they're not here at the end. So yes, this whole thing is going to come down as is, right? As is, or flip it. As is, but I'm going to multiply the whole thing by 3 because I need to have a correct quantity. So that's going to be, thank you, what's this? 3H2 gases plus 3/2 oxygen gas makes 3H2O. So liquid, sorry. Delta H is what? Negative what? Negative 858 kilojoules. So you take this and multiply it by 3. Okay. So then what cancels? 3 waters, 3 waters. So 3.5 plus 3.5 is 3. 3/2 plus 3/2 is 3. And then 3 oxygens over here canceled. And what's left? 2 B's, 2 B's, 3 H2 gases, 3 H2 gases, and B2H6, B2H6. So then what do I do with these? Add them. So that plus that plus that yields that, whatever that is. Okay, you got Hess's law times 2 under your belt. Indirect, meaning reactions, manipulate reactions, add to be a total target equation. So this is your target down here. And the other one was, how did we set up the equation for the other Hess's law? Delta H reaction equals summation of the products minus summation of the reactants. But those are delta H formation values, and where do you find delta H formation values? Back your textbook or in a chart, right? Okay, so I won't do bond enthalpy or bond association right now. I'll let you guys practice with this. I will leave this up here for you because I think I copied most of this for you, but this has a little bit of extra information. So in terms of what I need from you, enthalpy problem set, go ahead and we'll work on that right now so you can get your questions answered before you go. Skip around as needed. And I do have the Hess's law problem set, which is, let me show you where that starts. Lost my actual sheets. So we still have about, not quite 10 minutes, but 10 minutes. What? Plus C, you're talking about integrals?
Yes.
Yes. It's plus a constant, right?
Yeah.
Whatever the constant is. Yeah.
Very hard. It's gonna be the same thing with the delta H.
You're doing enthalpy problem set right now? 1 through Thank you, 1 through 9, and then you're going to do the Hess's Law problem set. It kind of goes from page to page. I'm just going to show you that where it is on my website too for homework. Focus, children. Focus.
Graded for that. I didn't see
For what?
no test. Sorry.
Oh, I haven't put the test grading yet. I have them graded. I just haven't put them in private school. I'll give them back to you.
Did I? Because I was 0 in the test. So I was asking.
Oh, are you talking about the
Test correction.
that one? I probably haven't put it in. Yeah.
Okay.
That one I will put in though.
I might have turned it into the wrong thing.
Because I don't think there's anything left. I know you turned it in, and if you turn in one of the other boxes, I'll get to it. I just haven't taken everything out of honors yet. Don't worry about it right now.
Okay.
All right, so you can see for homework today and tomorrow, this is a combined homework day. Complete the rest of the enthalpy problem set and Hess's Law problem set. Does everybody know where Hess's Law problem set is in your packet? It goes from like page 2 to page 3. The answers are at the bottom, not at the bottom. Nope, no answers. This is just a sample, and then you're going to do some questions related to it. Redox corrections, due on Wednesday. This was assigned last week. Don't do number 1. Number 1 is a really hard balancing oxidation state change. You don't really need to focus on that. Focus on your other things. And then your labs. Your labs, if they are not, the old ones are not 100% done, I can only give so much time for that, right? So tomorrow is probably going to be like double check AP Chemistry Day, make sure everything's done, okay? So if you need help with labs, you gotta ask me, text me, email me. I'll be in professional development all day, like we have a full work day. So just know that I will get back to you. Just won't be immediate.
Or you could be next Monday.
Next Monday, I have to get through a conference. So yeah, you'll see next Monday.
Yeah,
I'm
I
not
saw
here.
that this morning. I was looking at it.
Yeah, I have to run a conference at UNC Charlotte for permanent chemistry.
Because at first I thought it was today, and I looked at it this morning. I was like, I just saw it. I was trying to get
No, no.
I actually gone that. I was confused.
No, I have to run a conference, so I have a grant I have to prepare for.
Which one we not doing?
Number 1, so this is redox corrections due. This is your test corrections from redox. Number 1, that first one, that's a balancing. That was really difficult, so just skip that one and do everything else.